Hello teacher, today I will talk about an interesting experiment we did using something called Maria bottle. This device is very useful because it can keep a constant water level and flow. Our experiment have two main goals. The first is find the exit velocity of water when it flows out of the bottle. And the second is estimate the value of gravity using our measurements. We use different scientific formulas to understand the movement of the water. This includes Bernoulli's equation to relate the pressure, the speed, and height, the continuity equation to show how fluid flow is constant, and the Torricelli's principle to calculate water speed based on height. I will explain step by step what we did. What is a Maria bottle? The Maria bottle was named after Ed Marriott, a French scientist. It is a special type of bottle that helps control the water flow. Instead of need a pump, it works using gravity and air pressure. This type of bottle is useful in irrigation systems. It helps keep water flowing at a steady rate, which is very important for watering the crops in places where water is limited. Now, let's move on to how we build the Maria's bottle and test it. First, the experiment setup and procedure. To perform our experiment, we built a Maria bottle using a plastic bottle of 3 liters of capacity, PVC tubes for draining the water, and air pressure regulation, and measuring tools like ruler, stopwatch, and makers. In the first part, we measured the exit velocity of the water. We record how the water level dropped over the time and use the continuity equation to calculate the velocity. And in the second part, we raise the central tube at the different heights to observe the change in the velocity and use a linear regression to estimate g, the acceleration due to gravity. Results and analysis. Exit velocity measurement, we found that the water exits the bottle at a constant velocity. Our experimental value was 1.2 plus minus 0.3 meters per second, compared to the theoretical 1.144 meters per second with a 4% of discrepancy. Now, the estimation gravity. Using the least square method, we obtained that g equal to 10.65 plus minus 0.0005 meters per second squared, which is a significant higher than the accepted value that is 9.81 meters per second squared. In conclusion, this experiment helped us to understand the fluid dynamics and verify fundamental physics equations. Despite some discrepancy, we successfully demonstrate how the Maria bottle maintains a constant hydraulic head, and how it can be applied in a real-world system, like gravity-fed irrigation.